So I'm not really sure how I'm supposed to follow Ron and VJ. I don't have any nice pictures really in my talk. It's actually a very humble, slow, probably very short, even rivaling Ron's talk in terms of minutes presentation. So maybe I should have seen VJ and Ron's slides before I started mine. Okay, so I'll be talking about high performance and robust distributed sparse direct solvers for a few minutes. So what do I mean by that? That's a whole bunch of words. So starting in sort of reverse order, the sort of solvers that I tend to focus on more over time, it's a sort of particular class, like dense and sparse linear and eigensystems, dense and sparse generalized least squares problems, and then as of recently working on some conic optimization. And so these sorts of solvers, especially I tend to focus on direct algorithms for them. This is something that I think is increasingly being somewhat abandoned in the world of large-scale computing. Everyone, especially in Silicon Valley, tends to always do first-order methods. I come very much from the engineering community, where if you want to solve a problem, you want it to 10 digits. It's a little bit different of an approach. So in that world, the sorts of algorithms that I tended to focus on would make use of very large-scale dense factorizations, either for dense matrices or sparse matrices. You may want to solve some sort of generalized least squares problem, approximating ax equals b plus some sort of regularization, maybe in the 2 norm. And then increasingly, since here at Stanford there's so much optimization work, I haven't been able to but help myself and start working on interior point methods. And so for those of you that aren't sort of in that area, it's pretty amazing how little software there's been for doing especially sparse problems for convex optimization on very large-scale machines. That's been something, for better or for worse, that I've been somewhat obsessed with since becoming a graduate student. And in particular, what I like to work on is robust algorithms for this. So to me, if I can come up with even a single example that is a nice problem that breaks an algorithm, I don't really like that algorithm anymore. I want to be able to prove something like, if you give me a matrix with a condition number less than 10 to the 8, that I can solve that problem to however many of digits of accuracy is appropriate, like let's say 10. And beyond that, I'd really like to work on software that's very high performance. So in particular, if I gave you a machine like at the bottom, this is where I tend to focus. So there's a library that I've worked on for a long time that I've spent entire summers doing nothing but benchmarking on 10,000 cores of supercomputers, solving these sorts of problems. So in fact, one of the original sorts of problem that, for instance, national labs care about a lot is if someone gives you a really large matrix A, which might be a Hamiltonian, and this matrix B might be some sort of artifact of whatever basis you discretized your Hamiltonian with, you'd really like to compute all of the eigenfunctions x and maybe eigenvalues lambda of this matrix. So this is something that actually crunches pretty continuously all the time for density functional theory, and it was kind of my entrance into national labs working on these sorts of machines. And so there are people that do nothing but work on these sorts of algorithms and write software for it. In fact, very big projects. But I'm kind of a little more demanding than that, and in fact, I'd like to be able to do everything like that on these sorts of machines. Suppose someone gave you a giant sparse matrix A and some regularization matrix gamma, and you'd like to do very large-scale Tikhonov regularization on tens of thousands of cores. There should be good software for this, but in fact, it's kind of surprising that there isn't. In fact, as far as I'm aware, I'm the only person that's even written software to do this directly on those sorts of machines. Another thing you may want to do is suppose you're thinking about solving an eigenproblem, but it's not actually a sort of a nice operator. So for those of you that do a lot of linear algebra, suppose someone hands you a non-normal operator and they ask you something about the eigenvalues. So this is a common question in a lot of different fields. But in fact, it's often not a very well-defined thing. In fact, just transposing the matrix and computing the eigenvalues again, you might get something very different due to just very small round-off error. So something that you may want to compute instead is, well, what are the sort of disks surrounding what would have been the eigenvalue? Or if I perturbed the matrix just a little, where could the eigenvalue have gone? So there's something people call pseudospectra, which you might define, say, the epsilon pseudospectra of a matrix A to be the entire region in the complex plane where if you perturb the matrix less than some value in the P norm, that you could make it singular. So another way of putting that would be if you looked at the resolvent operator, say the inverse of A minus that shift in the complex plane, and you look at its inverse, is its P norm greater than some value 1 over epsilon? Where as epsilon goes to 0, you return just to the eigenvalues of this operator. So I've spent a while, and in fact, right when I came here, one of the things I was very actively working on was how could I compute this very quickly for a large window in the complex plane for actually a very, very large matrix. Okay, and increasingly the sort of thing that I'm being sort of pulled towards is doing more optimization. In particular, if someone handed you a machine like this and asked you to solve a large sparse quadratic program or second order cone program or, God forbid, like semi-definite program, there's absolutely no software that will do this to, let's say 10 digits of accuracy for a sparse matrix. There's been, a little bit of work. People will have publications on doing quadratic programs for sparse matrices on these sorts of machines, but no open source software ever seems to appear from that. There's been a little bit on semi-definite programs for dense matrices, but in general, there isn't just a suite that you can use. If someone hands you a giant, say, regularized least squares or optimization program, that you can just solve it on one of these machines. And so I'm very demanding, and I want this software to exist, so I just work to make it exist. Okay, and so part of that work is what I would call my firstborn child. So if you actually looked at the commit logs for this, it's kind of criminal almost. I think I've committed more than a few million lines of code to this since I started it, which I don't want to compute the man hours that I've put into this, but it's something astronomical. And so it's actually all open source, and I pretty regularly work on this. And basically everything I just talked about, there are open source and in fact BSD licensed implementations for that you can run from, say, C++ or Python on actually very large machines. And I think increasingly I sort of feel like it's me against the world with this style of algorithm. I think basically all of Silicon Valley no longer does this style of work. I care very much about it, and I think it makes sense from the perspective of solving an engineering problem, but if you want a few digits of accuracy, you do something very different. So, as I said, I'm very stubborn. So in fact, right now, this software stack you could think of is going up to very large sparse quadratic programs. The next step would obviously be doing second order cone programs, which might help. If you have a quadratic term that's actually low rank, you could use, say, a second order cone program to solve it more efficiently. And increasingly, in fact, when I look at a lot of the open source projects that exist where people demand optimization, I almost always see someone really want a high performance mixed integer program solver. And by all means, that's not something I've worked on before, but sort of extrapolating out where I expect to be in a few years at some point, I'm pretty sure I'll be working on that. And as I said, I also have very demanding with this style of software, and so I'd also like it to run efficiently on the biggest machines I can get my hands on. Also with, even if it's 10,000 cores, increasingly any of these types of machines will also have, say, GPUs, and so I'd like this software to run efficiently there as well. So as I said, I put together a very short talk. If you're interested in any of this, you can go to either of these websites. There's a GitHub page where I might actually be embarrassed if you look how many times I've committed in the last 24 hours. But if you have any questions or comments or criticisms, I'm happy to take them. Thanks.
Hey, questions or comments or criticisms?
Or concerns. So I think it's a chicken and egg problem, to be honest. It's not like people haven't wanted to do this for a long time. There have been papers on this for 20 years, but for whatever reason, no one's pushed out open source software that's of high quality. I think people have honestly preferred to start companies. So I'm a little stubborn in the fact that I don't want to start a company, at least not yet. so I'm still just releasing the software, in fact, as I write it. So I'd say maybe it's a little bit, it's not that people aren't able, but I might be one of the few people that's actually written this style of software from the ground up. So I actually wrote the dense solvers to the sparse direct, to the interior point, and the whole stack, versus, for whatever reason, I think the high-performance computing community tends to like to be segmented. One person likes to say, I do dense, and I do sparse direct QR, and I do, for whatever reason, there are these boundaries, and I think that oftentimes you really have to cross all of these different boundaries to produce something that's, solving like a sparse QP efficiently, if you want it to be robust. Any other questions? Uh-huh.
What I remember about doing when you have these massive clusters is that there are several kinds of them. You can have, like, as you said, have like tens of thousands of GPUs, or you can just have distributed computers, like the setting program. The thing is that, does your library scale to the various types? Because I've learned that humans do very specific algorithms depending on the architecture of the tool you're using.
So, I mean, asking if something scales is honestly kind of a vague question. What do you mean by, does it scale to it?
I mean, it's just that an algorithm that is distributed between a couple of computers and an algorithm for GPUs tend to be extremely different. Does elemental include variations depending on the type of hardware?
Right, so the abstraction I like to think of is that you have things that are intranode, where you might think of running your BLAS and LAPACK in sort of low-level linear algebra, and then above that is where I like to live. So I have spent actually a considerable amount of time writing kernels just to do, for instance, dense matrix multiplication on a GPU. I'm not naive to it, but there's a nice separation of concerns where, frankly, I think on node you need something like dynamic scheduling to do your dense linear algebra, et cetera, use your GPU effectively. Because suppose I have 8 cores in one GPU. Well, it's not homogeneous anymore. However, if you abstract above the node, where each node is one entity where you do your linear algebra, then in fact now you have a homogeneous system again from the perspective of someone working above the node. So that's sort of the way that I think about it. And from that perspective, it's actually, with a nice communication library, you're fine. And you can work on pretty abstract machines, with the exception of something that's actually very simple that I don't think people have properly tried to solve, which is, suppose I just gave you 2 different matrices of different sizes, and I asked you to, I don't know, compute their eigenvalues at the same time on one machine. People avoid this problem at all costs. And the typical thing that they'll do is always demand that they only cut the network in half. Either you cut it in half or you don't cut it at all. This is a pretty robust way to handle this sort of problem. But obviously, if someone gave me 10,000 matrices to diagonalize because they want to see if they're in some semi-definite cone, well, that I think there's research left to do where people need to come up with something like a smart static scheduler that's aware of the network. And there you're right, you need to be aware of the network. But if you have sort of load balanced operations where you know a priori that maybe you have like a binary tree, which is often the case in sparse direct solvers, then you can be very robust in your performance.
Any more questions? Well, thanks very much
Okay,
again, Jack.
thanks.